All right, so we're going to skip ahead. And then for the benefit of the video, I'm just explaining that we figured out why in problem 14.3 the inverse cosine of x naught over a didn't give us the right angle for the phase because it should have been negative. And we drew a picture making our one-dimensional motion into two-dimensional motion, like the Jupiter orbit thing. And this is a redrawing of that. And we realized that since the cart's moving to the right, the angle had to be negative 53 degrees and not positive 53 degrees. All right, so the next thing we're going to talk about is energy in simple harmonic motion. So our two flavors of energy are potential energy and kinetic energy. The symbols we use are U for potential energy and K for kinetic energy. They both have units of joules. So this is very similar to when we were doing spring potential energy back in 221. So we said there were two forms of potential energy in motion. There's gravitational and there's spring. Since we're dealing with periodic motion, then we use the spring potential energy. Even if we're not necessarily using a spring in our system, you can think of any periodic system as having some form of springiness or a restoring force, essentially. So even a pendulum is periodic because there's a restoring force that's pulling it back to the origin. In that case, it is gravity, but it works in the same way as having a spring on our oscillating mass. So if we remember back to 221, when we did spring potential energy, we said U spring was 1/2 k x squared. Does that ring a bell? It was a long time ago for most of you. So now we're talking about x changing as a function of time. So x just becomes x of t squared. Okay? So you take your x of t equation, which was a cosine omega t plus phi, and square it. Then you get kind of something ugly. All right, and then kinetic energy, it's always been 1/2 mv squared, even when we were in 222. Wait, did we use much with kinetic energy in 222? Actually, that doesn't really come up much in circuits. Yeah. All right, so K of T is 1/2 mv squared. So then you get m omega squared, a squared, sine squared, blah. That's kind of ugly. So what I can do is actually take this m omega squared and get rid of it. This is 1/2 m omega squared, a squared, sine squared, all that. And if we remember, omega is the square root of, was it k over m? So if you square that, and rearrange this, then m omega squared, so that over here, equals k spring. No, k spring, not squared. Everyone see that? How m omega squared equals k spring? Okay, so that's what I'm going to get rid of in there. Do that substitution. So now I have 1/2 k spring, and then a squared sine squared omega t plus phi. This was 1/2 k spring, a squared cosine squared. Okay, so now they're looking a lot more similar. 1/2 k spring, a squared, cosine squared, sine squared. So that's the only difference. One's cosine squared, one's sine squared. So visually, if you square a cosine function, instead of being going positive and negative, it just shifts it up so it's all positive. it's actually more like this. If you take, this is the cosine function. If you square it, it's kind of like taking anything that was negative and making it positive, but not quite that ugly. So it's like this. So it's all positive, but it's very periodic in its motion. And you'll notice that this cosine squared function has twice the period of the, twice the frequency of the cosine function. So that's important to note. Okay, so then the sine squared function is just going to be the inverse of that. So as we've learned before, as kinetic energy increases, potential energy is going to decrease. So they're always inverses of each other. And if you add up at any given point in time, you add these up. Like at this point, you've got half kinetic energy and half potential energy. So the sum of the two is going to be this line up here. So if you add up at any point in time, your total energy is a straight line along the top. So your total energy is constant. It's the sum of the two. So how do you get this plus this equaling a constant? Well, that's that trig identity we used before. Sine squared plus cosine squared equals 1. So your constant total energy is just the 1/2 Ka squared term. So turns out trig's been pretty useful tonight. As much as we don't like it, try and forget it. Okay. So I'm going to add below our position graph an energy graph to show how for every one cycle of position we should have 2 cycles of energy, which is really kind of tricky to draw. So this is our total energy along the top. So that's 1/2 Ka squared. So every time there's a peak or a trough, we have a peak on our cosine graph. And those of you who checked out the lab, I need to print the lab. Huh. Like those of you who have the lab, there's no labs there. When I'm drawing, actually what I have been drawing is pretty much what you're going to do in the preliminary questions of your lab. So just FYI. So this was our potential energy graph, and kinetic energy is opposite of that. Okay, so we see one cycle of our position graph. We've got 2 cycles of our energies. It's kind of crazy looking. So questions about that? Okay. This is a visualization of the same thing, just showing that at various points along, this is an oscillating block at various points along its path, how it's interchanging between kinetic and potential energy. Okay, so for our position graph, at which of the following times is the potential energy of the spring the greatest? Okay, who's ready to vote? Okay, I think everybody raised their hand, though some people tentatively. We'll go for it. Who thinks it's A? B? C? D? All right. Everybody is correct. So you guys were not sure, but you were all right. So the next one is the same question, except where is the kinetic energy the greatest? Who's ready to vote? Okay, who thinks it's A? Who thinks it's B? Almost everybody. Who thinks it's C? One vote. Who thinks it's D? Okay. Justin, why were you so excited that it was B?
Because it's really easy, because it's a feeling.
You've been swayed? Okay, John's been swayed. Okay, everybody's convinced? All right. So it's more than one of the above?
Because wouldn't 1/8 and 3/8 be the same? Aren't those both at the midpoint?
Let's see. So this.
Oh, those are quarters. Never
1/4.
mind.
Oh, yeah. Red herring. So, yeah. All right, so we're all convinced? The answer was B? Okay, the book agrees. All right. So problem 1414. To be super creative, this is the same glider we've been dealing with previously.
Wow.
Yes, I know. So you can spend a few minutes in your groups trying to find max acceleration. What is this? Some other questions. So we'll see how you guys are doing on this in your groups, and if you guys are getting stumped, then I can do stuff on the board. And while you're working for the next 5 minutes, I'm going to turn the video off.